Hello students. So in the last class, we have started a new chapter that is mass spectrometry, and I already explained the basic concept of mass spectroscopy here. So introduction and uses, advantage and principle. This all are explained, already explained. And now the another important concept is the instrumentation. So instrumentation of the mass spectra is very important, and here you can see the instrumentation here. So it looks very small, but it's very costly one, and for maintenance also is very costly here. So in the picture you can easily note some bottles here. That means these bottles, they are the reference bottles, and the compound they are introducing to the sample here. And here it looks like a CPU. So that means here data analyzes and it gives a result. So the total process is takes place in this, and this is about the diagram. So but the principle, the instrument have its own different parts, the components, and it have its own working principle here. So in the first, the instrument used for the recording of mass spectrum is called mass spectrometer. So here the instrument it is used for the recording of mass spectrum is called mass spectrometer. The mass spectrometer is designed to perform the following function. The function means the functioning of mass spectrometer means to design the basic designs. First, to vaporize the compound. So before introducing the compound into the mass spectrometer, so it must vaporizes into the mass spectrometer. So first one is the vaporized compound, and then to ionize the molecule to produce parent ion and fragment ions. So next one is to ionize the molecule. So they ionize the molecule in to produce the parent and ion fragments. So and third one, the differentiate ions according to their M by E ratio. So here the third one, the differentiate ion. So that means the ions are differentiated into on the basis of their mass and charge ratio, and to detect the ions and to produce signal as per their relative abundance. So at the end, the differentiated ion, that means ions are accelerated on the basis of their M by E ratio, and then it is detected, and ions is detected and it gives the signal. So this signal here, it is noted here. Okay. And then the components of the spectrometer. So here the sample, it have the some important components. They are sample injector, ionization chamber, mass analyzer, ion collector, and amplifier, and then the recorder. So here sample injector and ionization chamber, mass analyzer, and ion collector and amplifier and recorder. So here you can see a block diagram. That means it is the block diagram. So sample injector means here, as the name says, it injects the sample. So different sample have different character. Their physical character may changes. Their some of the chemical characters also vary. So they have. So because of this, we need a sample injector here, and then ion source. So here the ion source means they produce ions here, ion source. That means the sample, after the injection of sample, it produces the ion, and then mass analyzer. So here the real mass spectrometer analyzing takes place here, and then ions are detected. That means ion producing ion source from the sample, and then it is detected in the ion detector, and then signal sensor. That means the ions detected, and then they are converted to their signal. So they are converted to signal, and then it is recorded. So it is a block diagram. So this block diagram is enough. So for the exam, and then first part in the component we saw sample injector. So in the sample injector, it is introduction of a sample into the ionization chamber by following two methods. That means it normally follows two methods. Which one? One is external sample introducing system, and one is internal sample introducing system. So as the name says, the external sample introducing system means in the picture you can see. So they are sample injected here. See in the bottles. So here the bottles, they are here we have the bottles of reference and sample here. So they are injecting the sample here. So the external sample introducing system is applicable sufficiently to volatile compounds at 373 Kelvin to 873 Kelvin. That means in this temperature, if the compound is volatile, so if the compound is volatile, so then this technique, that means external sample introducing technique, we can follow. So here 10 to 10 gram. That means here the sample, normally 10 gram of sample is enough. And then second, internal sample introducing. So sample is placed within the ionization chamber either as a part of the ion source or a coated on a filament. So here the sample, if it is not volatile in the range of 373 to 873 Kelvin, then we have to move on the second one. That means it is coated inside the source, ion source. So it is coated inside or it is placed inside the ion source. So here directly we are introducing the sample inside the ion source. So this is what we call the internal sample introducing system. And first one is external sample introducing system. And then ionization chamber. So it have some common source. That means for the different source of ion, we have different methods. So here, for example, electron ionization, EI. So here the gas phase is normally they are used in the gas phase, and energetic electrons there. So ionizing agent is energetic electrons, and then field ionization. So here field ionization Fi, gas phase. So it's the type is gas phase, and high potential electrode. So here they are producing the ions by high potential electrode. And in the first one, energetic electron means they are bombarding energetic electron. And then chemical ionization, here also it is in the gas phase. Then the reagent is positive ions or electron capture. That means they are ion, chemically they are produce their ions here. And then fast atom bombardment. So here, as name says, energetic atoms, they are produced by bombarding of a atom. And then field desorption. So here desorption is the type, and here high potential electrode, here also they are using high potential electrode. And then laser dispersion. So here also the laser beam they are used to produce the ion, so ions here. And then plasma dispersion, secondary ion mass. So here they are have the different types. So just go through the types here. So this is the ionization chamber. That means ion sources are produced on this way. So that means we can produce ions on these different types. And then the ion source converts the molecule into gaseous ion. So here first thing, the ion source has its own um, character and function here. So the functions are the ion source converts molecule into their gaseous ion. And then second one, the most common way of producing ion involves here, the most common ions they are involves in the sample with a beam of energetic electron from the ion gun. So that means, so this is one of the method to produce the uh, ions in the ion source by bombarding the electrons to the sample. So then it produces the ions. And then the electron ionization, EI, short form. So here the technique electrons, that means in this technique, electrons are accelerated from hot tungsten filament to an anode, usually through a potential difference of 70 eV. So here what happens, they are normally the electron ionization, they are using tungsten in the volt of 70 eV electron volt. So they are normally which produce the or accelerate the ion movement here. And then the chemical ionization. The chemical ionization, so Ca, a reagent gas like methane or butane, ammonia is allowed to pass into the ion chamber at the pressure of 10 to sorry 102 nm to 2. So here this is the pressure, and here the as the name says, they are chemically they produce the ion sources. And then last one, disproportion. So here type use sample probe from the which energy directly transfer ion or a molecule in the condensed phase to ion. So here it is in the condensed phase they are producing the ion. So here Fi. So here Fi means what? Feed ionization. Feed ionization, and then Fd means here feed dispersion. So here field desorption. So here employs large voltage of produce large electric field to ionize the molecule. So here they are using the large electric field they are used to produce ions. And then FAB. So here fast atom bombardment. So here the fast atom bombardment FAB, the sample in the condensed state. That means sample is normally in the condensed uh, state and then mixed with the glycerol. So it is mixed with glycerol and is ionized by bombardment with the energetic Xe. That means here xenon or a helium atom. So they are bombarded with the xenon or helium atom. They are neutral atom, but they have the high speed movement. So it is another method. And the ion produced are repelled out of the source by using small repeller voltage transmitted through the accelerating potential and injected into the mass analyzer. So the ions produced are repelled out of the source. So now this much method or a technique they are used to produce the ions. And after the production of ions, we have to move or we have to pass the ions, produced ion through the analyzer. So what they will do, they give us some amount of volt or a current to the source. That source means the ions produced. So for that ions produced, for example, the ions are positively charged ion means they are produced or a supply a small amount of voltage throughout the source. Now what happens? The ions also positively charged and the source, the surrounding source chamber also positively charged. And then what happens? This ion get repelled from the ion source and it moves to the next analyzer. So here you can see. So if it is source means here the ions are produced and then it is repelled and it moves to electrostatic analyzer. So here we have the analyzer. This is the analyzer path. So it is have the 180-degree path. Okay, and here it is produced source. Here the source are produced and then it is repelled because of the small voltage and then it is analyzed. Here, normally two types of analyze are there: electrostatic analyzer and magnetic analyzer. So here, the two types of analyzer, one is electrostatic and one is magnetic. And here, in the next part, we can easily understand what are analyzer and their types here. The accelerated ions travel in the circular path, as I said. So you can see in the diagram, it is circular path. So it is circular path. Is a circular path. This ion first of all passes through the slit and enter to the electrostatic analyzer. So first what happens after the production of ions, it passes through the slit and it enters the electrostatic analyzer. And then the ions then passes into the magnetic analyzer. So second, it passes through the magnetic analyzer. The ions of particular M by E are resolved. So here, the particular M by E, that means mass by charge ratio, is resolved here. And then detector and ion collector. So what happens in the next? The detector detects the ion and then it falls on the detector and then it is detected and the ion current is produced, and that means after the ion detected by the detector. So some current or a charge produced. So in the collector, the ion current is amplified. That means it is amplified in the detector and direct current amplifier. So recorder records the peaks. So after that, it produces the signal. So this signal gives the peaks. That means records of the peak, and the spectrum is recorded by using fast scanning oscillograph. That means so here their spectrum is recorded by the scanning, the fast scanning of oscillograph here. And then this is about the mass spectra. So sorry, mass spectrometer. So this is also a 4 mass question, important question. After that, we have the mass spectrum. So the mass spectrometer is different. Mass spectrum means after the production of the graph here. After the production of the graph, so here what happens up to here, this is the part of the spectrometer. After this, we have to analyze the spectrum. That is the result or the recorded data of the spectrometer. We will get here, and then we have to analyze. To analyze this peak, so normally it gives in the form of peaks here. Here we have the example. Here you can see these all are the peaks. So in this type, we have the graph. Okay, and then mass spectrum, it is a flow relative abundance of ion against m by e ratio. So the graph is the relative abundance. That means the number of availability versus mass to charge ratio. So the graph is like this. The graph is relative abundance versus mass to charge ratio, m by z. So in this, for example, 41 mass by charge means the molecular mass of 41, abundance is 40, like this. Or molecular mass of 55 with the abundance of 80. So that means 80 percent it is present. So like this we can say it is the its abundance here. Okay, and then there are a series of vertical lines which indicate the ion intensity. So as I said, the intensity, the vertical line shows the intensity, how much or how dense the ions are there or are present, so that we can identify. Then the important peaks have m by e value written at the top. So only the important, here we have lot of peaks here, but only the important peaks. That means these are the characteristic peaks. They have the molecular mass or they have written with the m by e values here. So this is very important. Which one have noted with the m by e values or mass molecular mass value. So that's very important. And then some of the important peaks are as follows. So for that, we have some of the important peaks. First one, the base peak. So it is the most intense peak. Normally, it is most intense peak, and it is assigned 100% intensity, and the intensities of other ion, including molecular ion peak, are expressed as a percentage of the base peak. So here what happens, the base peak means normally here you can see here, this is the base peak here. So this is the base peak. So it is highly intense peak. So you can see in the picture. So it have the highest intensity. That means the tallest among all the peaks here. So it is the highest peak. So it which have highest intensity. So this is the base peak. Okay. And then normally what they will do, they assign the base peak as the 100% intensity. So that means they prefer or they noted this base peak with the highest intensity as 100%. That is the maximum intensity in a compound is highest. That is, it is the 100% of intensity. And then they are comparing, for example, this much of compound with the 100 base peak as the intensity. And then what about this peak? They are compared with this intensity and then this intensity, and to calculate the abundance, relative abundance. So that means the relative abundance means what? The relate the abundance of other compound or other ion with the base peak. So it is called relative abundance here. And then it is intensities of other ion, including molecular ion peak, are expressed as the percentage of base peak. So here, in some cases, the molecular ion peaks or parent ion peak, their base peak, both are same in some of the cases. In some of the cases, they are different. For example, the molecular ion or parent ion peak. The molecular ion or parent ion peak. So here you can see this is the molecular ion peak. That means if we have the compound of M, after the bombarding of the compound with an electron, what happens? It gives M dot plus or a M dot. So this is the ion formation with the M dot. Okay. And this is what we call the parent. This is the parent. And here the ions are produced called the parent ion. And this is what we call the parent ion peak or a molecular ion peak. So this is the molecular ion peak. Normally here we have the reaction here. This is the reaction M. After the bombarding, it produces a ion here. The peak corresponding to this ion is called as molecular ion peak. So this is the this peak here you can see. So this is the molecular ion peak. And then highly relative compounds may not give the molecular ion peak or may give the peak of low intensity. That means highly reactive. If the compound is highly reactive means after the production of parent ion peak, so it produces suddenly it produces its daughter ions. That means it's smaller m. Okay, it's already we discussed m1 and m2. So we can expect only half or little amount of the parent peak here. So its intensity is lower than the base peak in some cases. It's not in all the cases. So its intensity peak will vary here. And then next one, isotopic peak. So what is isotopic peak here? As the name says, the peak which gives the idea about the isotopes. So isotopes. So here you can see the isotopic peak. So here the parent ion peak, and it has some smaller peak here. That means is near to the molecular ion peak. So here that it gives the idea about the compound with the small amount of isotopes. That means the isotope means they have the higher or lower molecular mass than the parent ion. So same molecular atomic number but different in the molecular mass. So from this we can expect this type of small peaks nearer to the parent peak. So this is what we call isotopic peak here. Each of the carbon, hydrogen, nitrogen has the principal heavier isotope, and presence of element in the compound will give the a small isotopic peak. That means M is the molecular mass of parental peak, but we can expect a small peak. Here we can already I noted here. So expect a plus one. That means nitrogen with the or carbon with 12 atomic mass number, but we can expect a 12 plus 1. That means a small peak in the 14 we can expect. So that is what we call the isotopic peak. For oxygen, sulfur, chlorine, bromine, principal uh, heavier heavier isotope is 2 mass unit greater than the most of common isotopes. That means in the oxygen, sulfur, and chlorine, they have 2 masses. That means they are not plus 1, it is plus 2. That means after the uh, 2 masses, then that means the difference between the two isotopic mass and the parental peak, it is 2 here. So we can expect the peak next to them. So here you can see, so this is the one abundance. So this is another one. And next here. So first difference is plus one. That means is next to the parent peak. And another one, this one is the plus two ion. So here the plus two and plus one isotopic peak. So in the picture you can see the isotopic peak are useful for determining the molecular formula of the compound. To identify the molecular formula is very important here. For example, carbon, hydrogen, they have their own isotopic peak. Then we can easily identify their molecular formula. So here it's about the isotopic peak. So in the next, we have the metastable ion. So in the next class, I will explain about the metastable ion. So I will finish here. Thank you.